കാണാൻ പറ്റുന്നുണ്ടോ? കാണാൻ പറ്റുന്നുണ്ടോ? ഓക്കെ. അപ്പൊ എന്തായാലും നിങ്ങൾ ക്ലാസ്സിന്റെ ഇടയിലാണ്. ഞാനും എനിക്ക് പറഞ്ഞ പരീക്ഷ ഡ്യൂട്ടി ഒക്കെ ഉണ്ട്. 1 മണിക്ക് എനിക്ക് ഫ്രീ ആവണം. അപ്പൊ അതുകൊണ്ടാണ് ഞാൻ 12:30 തന്നെ ഷാർപ്പ് കയറി വന്ന് റെഡിയായി വന്നത് കേട്ടോ. എന്ന് വെച്ചാൽ എല്ലാരും തിരക്ക് പിടിച്ച പണിയിലാണല്ലോ. എനിവേ നമുക്കുള്ള സമയം കൊണ്ട് ഡിസ്കഷൻ ആരംഭിക്കാം. സ്ക്രീൻ കാണാൻ പറ്റുന്നുണ്ട് അല്ലേ? ഓക്കെ. ഓക്കെ, നമ്മൾ ഇന്ന് ഡിസ്കസ് ചെയ്യുന്നത് മൾട്ടിവേരിയറ്റ് ഡിഫറൻസിയേഷൻ ആണ്. റെഡിയല്ലേ? I think you have studied the differentiation technique in your degree classes. That is available in the book of Bartek. Okay, this is the preliminary details of differentiation, derivative of a function. Function f is said to be differentiable, or f is called a derivative of, sorry, f dash is called a derivative of f if, or L is called a derivative of f if mod f, whenever mod x minus c less than delta, then mod f of x minus f of c by x minus c minus L less than epsilon. So that means f dash of c equal to limit x tends to c f of x minus f of c divided by x minus c. That is the derivative of the function at the point c. Okay, if this derivative exists, we say that the function f is differentiable. If this limit exists, okay, limit exists means the both the right limit, left limit, and function at that point exists. If the limit exists for f of x minus f of c by x minus c, then we say that the function f is differentiable. Okay, this is an example. X square, we can differentiate x square and we will get the answer as 2x. That is, you know all these results because you have studied in your degree classes. So you can read this chapter, derivative, chapter number 6, differentiation. Okay, and try to understand the univariate differentiation technique. There are some theorems related to differentiation, sum, product, difference, quotient, etc. Differentiation of sum, product, quotient, etc. And you can read and understand the univariate concept. Anyway, we are discussing, actually in this semester, we are discussing multivariate differentiation. So we have domain of the function d, where d is a subset of Rn, and range of the function is r raised to m, and let a is vector a is denoted as a1, a2, etc. an prime. It is an interior point of d. And suppose that limit we are setting limit hi tends to 0 in the case of ith variable. We are setting the limit as limit hi tends to 0, f of a1, a2, etc. ai plus hi, comma, etc. an minus f of a1, a2, etc. ai, comma, etc. an divided by ai plus hi minus ai. That is nothing but hi. Okay, so the numerator is difference of the function evaluated at ai plus hi and function evaluated at ai. Only the ith component is considering for the differentiation. And in the denominator we have ai plus hi minus ai. That is nothing but hi. So this is a derivative. Okay, this is a univariate derivative, and this derivative is usually known as partial derivative. Okay, that is denoted as dou f of a by dou xi. or we can denote it as fxi of vector A, as we seen in this figure. Okay, this is possible for every variable, that is I going from 1 to n. Hence, it is the partial derivatives of the function with respect to the variables. Okay, here we have an example, that is f of x1, x2, x3. The domain is three-dimensional domain, and domain itself is three-dimensional Euclidean space, that is x1, x2, x3. That vector x1, x2, x3 belongs to R3. And the range is univariate because the range value is x1 plus x1 into x2 square plus x2 into x3 cube. That is univariate. Okay, so we can differentiate with respect to x1, x2, and x3. What happens? Dou f of x by dou x1 equal to x2 square. Clearly, the first term contains x1 and x2 square. So when we differentiate with respect to x1, we get x2 square. Similarly, dou f of x by dou x2 is, from the first term we will have 2x1, x2. From the second time we will have x3 cube. From the third term we will have dou f of x by dou x3, that is equal to 2x2, 3x2, x3 square. Okay, so these are the partial derivatives of function f with respect to x1, x2, and x3. We can arrange these partial derivatives in a vector form. Okay, we can arrange because here we have only one component for the range function f. Suppose there are m components, that is the range of the function consists of m components of real numbers. So let it be f1, f2, f3, etc. fm. Okay, so domain is D, that belongs to Rn, and range belongs to Rm, and let the components be denoted as f1, fj, j from 1 to m. So we can find out the partial derivatives of these components with respect to all the components, and we can arrange it in a matrix form, that is denoted as, that can be denoted as jf of x. This will be an m by n matrix. What will be the components of the matrix? First row will consist of dou f1 by dou x1, dou f1 by dou x2, dou f1 by dou xn. Second row consists of the differentiation derivatives, dou f2 by dou x1, dou f2 by dou x2, etc. dou f2 by dou xn. Similarly, continuing in this fashion, we get the mth row, that is dou fm by dou x1, dou fm by dou x2, etc. dou fm by dou xn. That is usually denoted as jf of x. Okay, this is called a Jacobian, and jf of x is usually called a Jacobian matrix, and the determinant of jf of x is usually called a Jacobian determinant. Okay, that is Jacobian matrix. Jf of x is Jacobian matrix, and the determinant of jf of x is usually called Jacobian determinant. Okay, you might have heard about Jacobian of transformation when we study random variables, transformation of random variables. I think you have studied in degree classes to find out the distribution of function of random variables. So in that case, we will use the Jacobian of transformation. Okay, and the Jacobian determinant. So what is Jacobian determinant? Jacobian matrix is nothing but the matrix that arranged in such a way that each of the row contains the first partial derivative of each and every component, okay, of the function f from Rm to, D to Rm. Okay, so this is the Jacobian matrix, and the determinant of that matrix is usually called Jacobian determinant, and it is usually denoted as, for a simplicity, because instead of writing as a matrix form, we can write it as dou f1, f2, etc. dou fn divided by dou x1, x2, etc. dou xn. Okay, so that is notation. There is nothing with differentiation as we seen in equation number 7.8, that is a notation. Dou f1 f2 etc. dou f1 divided by dou x1 x2 xn. So that is the Jacobian determinant. Okay, let us try for an example to find out the Jacobian determinant. Okay, this is the application of this results is to find out the distribution of random distribution of functions of random variables. Distribution of functions of random variables. This result is applicable to find out the distribution of functions of random variables, or distribution of transformation of random variables. So in that theory, we will use Jacobian of transformation. So you have to study this mathematical technique in detail. So we consider an example f from R3 to R2, that is f of x1, x2, x3, that equal to x1 square plus cos x2, comma x2 square plus x3 square e raised to xn. We can take f1 as f1 of x is x1 square cos x2, f2 is x2 square plus x3 square into e raised to xn. So there are two components in the function. Okay, f1 and f2. f1 is nothing but x1 square cos x2, and f2 is nothing but x2 square plus x3 square e raised to xn. We can take differentiation with respect to x1, x2, x3 for both f1 and f2. What is dou f1 by dou x1? That is nothing but 2x1 into cos x2. What is dou f1 by dou x2? That is nothing but minus 2x1 square sin x2. What is dou f1 by dou x3? There is no x3 in f1, so it is 0. What is dou f2 by dou x1? Yeah, it is with respect to x1, x3 square into e raised to x1. What is dou f2 by dou x2? That is 2x2. There is no x2 term in the second term. What is dou f2 by dou x3? Only x3 comes in second time of the second function. So that is 2x3 into e raised to x1. So this is the Jacobian matrix. Okay. Note that in this case, the order is different, and we can find the Jacobian determinant only when the matrix is of same m by m or n by n. That means if m and n are equal, then only we can find out the determinant. So in this case, we cannot find out Jacobian determinant. Okay. So okay, yeah, this is the secondary higher order partial derivatives. Okay. What is so we shall differentiate again the first derivative with respect to another value. That is the procedure of finding second order partial derivatives. Suppose f xi, f suffix xi, a1 a2 etc. an denote first partial derivative of f with respect to xi. Again we take the derivative of this first partial derivative with respect to another variable xj, or xi again. That is the second derivative. Or we can take the derivative of the first partial derivative with respect to another variable xj, that is given in the second equation in this screen. In the screen you can see two equations. First one is the partial derivative of first partial derivative with respect to xi again. Second equation is partial derivative of first partial derivative with respect to another variable xj. Okay, these are called second order partial derivatives. What is the second order partial derivative of f with respect to xi? That is denoted as dou square f of a by dou xi square. That is nothing but limit hi tends to 0. F xi of a1 a2 etc. ai plus hi comma etc. an minus f xi of a1 a2 etc. ai comma an. That is difference of first partial derivatives. Okay. Again we are taking the difference. Okay. So divided by ai plus hi minus hi. Sorry, ai divided by ai plus hi minus ai, that is hi. So this is the partial derivative of f with respect to xi of partial derivative of first partial derivative of xi with respect to xi again. Okay. In below second equation, you can see what is that? We are considering partial derivative of f with respect to xi, and again we are taking the partial derivative of that partial derivative with respect to xj, so that we are writing it as limit hj tends to 0, because second time we are taking the difference with respect to xj. So limit hj tends to 0, f of xi, that is first partial derivative, a1 a2 etc aj plus hj comma etc an minus fxi a1 a2 etc aj. Note that there is the difference is taken with respect to j, xj. So aj plus hj comes in the first form, first function, and aj only in the second term. So minus fxi a1 a2 etc aj comma etc an divided by what is that, a plus hj minus aj plus hj minus aj, that is hj. So that is denoted as second partial derivative dou square f of x by dou xj dou xi, or it can be denoted as f xx xj xi a. I noted in the previous case it is denoted as dou square f of x by dou xi square, or f xi xi a. So this is the first and second partial derivatives. Okay. We have to prove one theorem. I told you we have what is that, 5 minutes more. So I am not trying to explain the theorem now. We will discuss in the next class, because it needs at least 20 minutes for the discussion, proof, etc. Okay. Anyway, we shall consider an example. Okay. First partial obtaining first and second partial derivative. Okay, let us consider this example. Consider f from R3 to R, that is f of x1, x2, x3, that equal to x1 e raised to x2 plus x2 cos x1. First partial derivative of this function. This is what is a univariate function. Sorry, what is that? A one-dimensional function. The domain is 3-dimensional, but the function is 1-dimensional. So we can easily find out the derivatives. Dou f x1, x2, x3 divided by dou x1 equal to what is that? E raised to x2 minus x2 into x2 into sine x1, because the derivative of cos is sine. Second is dou f of x1, x2, x3 by dou x2, that equal to respect to x2. So second term only. We have to apply the product rule. First function into what is that? Yeah, no need to apply a product rule. Just what is that? The derivative of e raised to x is e raised to x. So x1 into e raised to x2 plus x2 cos x1. So just cos x1. Yeah, that is the derivative with respect to x2. So what is the second derivative with respect to? We can differentiate the first derivative, first line, with respect to x2 again. So what will be the answer? E raised to x2 minus x2 sin x1. What is the derivative? Or just sin x1. Okay, because sin x1 is treated as constant with respect to x2. Okay, so first line, we consider first line and differentiate it again with respect to x2. We get e raised to x2 minus sin x1. And this is dou square f of x1, x2, x3 by dou x1, dou x2. Okay, first we differentiate with respect to x2. That is available in the second line. Okay. We can again differentiate with respect to x1. What will be the result? E raised to x2 minus, the derivative is cos is sine. Okay, e raised to x2 minus sine x1. So in this way, in this fashion, you can find out the derivative. Since there is no term involved, no term in x3, we will have 0 with respect to 0 for the derivative with respect to x3. So we are not displayed here. Anyway, there is one more variable x3, and whenever we differentiate with respect to x3, we will get 0 because there is no x3 term in the function. Okay, so we can find out in similar fashion. You can find out the second derivative also. Anyway, today we will stop here. You may try to find out second derivative of this. We have discussed two examples in the beginning of this session. Yeah, this one. You may try try to find out the second derivative of this function and this function also. Okay. Okay. There are two examples we have discussed for the first differentiation. You can try for second differentiation for these examples. Okay. Anyway, let me stop here because I have examination duty now. I have to